Unit 4 is about things that you would generally find in algebra. So, for what we're going to do, the right starting point is basically to start a little bit before functions. So, we're going to start with relations and then jump into functions, and then that's what most of Unit 4 is actually about. So, first things first, what is a relation exactly? Well, it's basically where you have two sets, where you associate elements in one set with elements in the other. And you can do it a bunch of different ways. You can kind of see the diagram peeking out for number one at the bottom there. You can do it that way. You can do it with a table. You can do it with ordered pairs. You can do it with a graph. So there are a bunch of different ways that you can do this. And then usually when you think about the domain and range, usually you think about the things in parentheses. I think, like most people think, domain is x values and then range is going to be y values. I think that's what most people think about. I guess in a general sense, maybe inputs and outputs is a little bit better. But I think if you think about it as x values and y values, you're going to be absolutely fine. Um, but I guess that doesn't really line up well with number one, but it will generally when it's not a diagram. So if we want to get the domain and range for number one, so if you think about that one as inputs and outputs, then just look at those arrows. So the inputs are what the arrows come from, and then the outputs are what the arrows go to. So you got the arrow that goes from oak to red, from the genus of the type of tree to the species. So oak is going to be part of the domain because that's one of the inputs that we've got here in our relation. And then red is going to be one of the outputs, so it'll be part of the range. And then so will white and so will sugar because arrows point toward those. And then maple will also be part of the domain since two arrows are coming out of it, right? So our domain then would be, I guess if I write this in set notation, I guess that might be the easiest thing. So I'll just write it as oak and maple as the two elements. And then the range. So what are the values that get mapped to in the species set over here on the right? It looks like it's red and white and sugar. So that's pretty much it. When you've got the relation set up this way, where it's the diagram, it's not too bad to pick the domain and range out. Another way to do it would be if you had a set of ordered pairs, like in number two, where there, if you think about the domain as being x values and the range as being y values, you're going to get the right thing. So here, our domain, if I write this in set notation, so for each of these ordered pairs, it's x comma y, right? That's how ordered pairs are written out. So the x values, if I just go from one ordered pair to the next, just left to right, and the first ordered pair, the x value is a -4. Second one, we got a -2. Then we got a 3. And then we got a 5. And then we got another 3. But from back when we did that set theory stuff in Unit 1, you don't need to write in duplicates. So that's our domain. -4, -2, 3, and 5. And then the range is going to be the y values. These aren't going to come out in order, but that's fine. We'll get 1, -3, -1, 2, and 0. I guess if you want to put those in order, you can, but it's okay to leave them out of order. All right, so that's another kind of different look that we can have for how a relation could be written out. But that's pretty much it. I mean, there's not too much else to do. Usually that's the way that they're written if they're just regular old relations. If they're functions, that's where you see graphs more commonly. And so that's what we're going to get into next. So functions are relations, but a function is only going to be a relation when each value in the domain is mapped to exactly one value in the range. So the thing that you can't have, and like if you're checking to see if a relation is a function, the thing that you want to look for, if I do this with a different color, it's right here, or one x value gets mapped to two y values. So you just look to see if that's going on. If that never happens, then you're good and you've got a function. If that happens someplace, then that's a problem and you don't have a function. So if you look at the first one, the thing that you got to look for that would cause trouble is if you have two x values getting mapped or one x value getting mapped to two different y values. I started to say that backwards. So then you just want to look at these and see if that's going on anywhere, right? You just look at the individual ordered pairs and see if you have two different ordered pairs where you have the same x value but different y values. So that's what we're looking for here. So that first one, if we look at those, our x values are -3, -1, 1, and 3. Well, those are all different. And if they're all different, there's no way you could have there's no way you could have one x value getting mapped to two y values. I keep trying to say that backwards for some reason. But this one is a function because the thing that causes trouble never happens. And the reason that this works is because all of the x values are different. So there's no way you could have one x value getting mapped to two y values, because in order to get that to happen, you would need two separate pairs where the x values were the same. And if that never happens, there's no way you can have this troubling scenario. And actually, this has a name, because if you look here, all of the y values are also different. So what that's actually called is a one-to-one correspondence, but I don't think we need to get into that. It's just that when you have a one-to-one correspondence, everything works the way that you want it to, which is nice, right? The next one, if we look at the x values, they're all different again. Because you got -2, -1, 0, 1, 2. Those are all different. And it's okay that like -2 and 2 both get mapped to -2. That's fine. It's okay if two x values get mapped to the same y value, just not the other way around. So this one is a function as well. And you can use kind of the same logic, right, to say that all of the x values are different. And if that happens automatically, you've got a function. And also, I figured I should probably mention this, so I'll put this in parentheses too, that it's okay that -2 and 2 both, oops, I missed the A, both map to -2. That's what I'm trying to write here. So both map to -2. That's fine. It's still a function. It's also okay that -1 and 1 both map to 1. So that's okay. The one that's trouble, and in number 3, again, just go through the x values. We got -5, 0, 5, 6, 2, and 2. That's the problem. Because if you go and look at that one, that pair and that pair, same x value, different y values. So 2 is getting mapped to two different things. So this is not a function. And the reason that that's not a function is because I changed color. Kind of. That doesn't look very good. And actually, I'll just make it purple so it sticks out more. All right, so the reason being is that 2 maps to both 0 and -5. Now I'm trying to write too fast. So 2 is mapped to both 0 and -5. So one value getting mapped to two different ones, that's when you don't have a function. And then the way I have 4 written is basically like the way that they look in the homework. There are questions that are just like this, where it says in which of the relations below is the output a function of the input. So if you think of the output as being the y values and the input as being the x values, then I think you'll be in good shape. And if we kind of look at what's going on here, so just go through the x values, see if any of them are the same, and then if they're the same, check the y values. So 3, 7, 8, and 3, The first and last ones have 3 as the x value, and they got different y values. So this is trouble, right? Because now we got same x value getting mapped to 2 different things. So this one is not a function for that reason. But then if you look at the one on the bottom, 0, -3, 4, and 9, they're all different. So that's okay. So then this one is a function. That one's fine. All right. Then what about if you have a graph? So if you have the ordered pairs or if you have a table, like these are pretty similar, right? Like the thing that we did with the table, it was basically the same thing we did with the ordered pairs. You look and see if they're a couple of pairs have the same x value, and then if they have different y values, you go, oh, not a function. What if you have a graph? If you have a graph, this is actually easier because you can use something called the vertical line test. If any vertical line intersects the graph in more than one point, then you don't have a function. And that would bear itself out with ordered pairs too. Because like a number, or number 1, an a of number 5, that's not a function, and you could just use the y-axis, right? Because that's going to hit that oval on the top and on the bottom. So that's what I would do with that one, is I would say if I drew in, like just right on top of the y-axis, if I drew in that vertical line, that's going to hit it in 2 separate points. And why does this vertical line test work? Because, well, what are the points that are on the top and the bottom? The point on the top is 0, 4, right? So like right there, that point is 0, 4. And then the point that's down here on the bottom, that point is 0, -4. So if you look at those points, they got the same x coordinate, different y coordinates, right? So now it's kind of like the ordered pairs when we had them listed out that way, or the table. So any vertical line intersecting it twice, that's trouble. So then this one is not a function because we have a vertical line that intersects that twice. We could pick other ones. If you pick the vertical line like x equals 1/2, I guess that would hit it in 2 spots too. But the easiest one to pick was the y-axis. So, right? No reason to make it harder for, just for fun. B, any vertical line is only going to intersect that once, right? Because this angular shape in here where it's straight across and then it kind of bends right at the y-axis. Any vertical line you pick, so like if I pick one out here, just going to hit it once. Or if I pick one over here where it's on the bend, right, like where it's angled downward, right on the bend, even that's okay, right? That's just going to be 1 point. So everything here is fine, right? So this one's going to be a function because there's no way that you can pick a vertical line that's going to intersect that twice. Then if we go down to where C and D are, C comes in 2 pieces, but those pieces don't overlap horizontally. Right? Because this piece on the left, it goes up to where x equals 1, and then the piece on the right starts where x equals 2. So because there's no overlap, any vertical line that you pick out here is just going to intersect at once. Any vertical line that you pick back here is just going to intersect at once. I guess you could be like right at where those points are. Then those are just going to intersect at once. So this is a function. The next one's not. I guess you could pick the y-axis again, and that's going to hit it 3 times. Or you could just pick something out here. I'm going to be different and just pick x equals -2. It's going to hit it once up there. And then down here it's going to hit it twice. So you only need one of them, right? You can pick that. You can pick the y-axis. You could pick, I guess, like x equals 4. That would work, right? Because you get that point, and then you'd get down here. In any event, there is a vertical line that exists that will intersect that graph in more than 1 point. There are a whole bunch of them. So that is not a function. So surprisingly, when it's a graph, I think this is actually easier, right? Because all you got to do is see, is there any vertical line that's going to intersect the graph in multiple points? If that's true, if there's one that exists, then what you have is not a function. If that doesn't exist, if every vertical line intersects it in only 1 point, or at most 1 point, then it's a function. So that's pretty much it for 4A, I think. It's just a lot of stuff about, is this or is this not a function? And then writing out domains and ranges. And that's most of what's in 4A. I think that's pretty much all of it.